Okay, hi, my name is Kelley. I'm a second year structural engineer working under Professor Shing's lab, and I will be presenting on a MATLAB-based analysis of the effect of transverse reinforcement on unconfined concrete. So before we begin, it's important to understand the objective of this research. So concrete is a very important material, and basically almost every structure that we walk inside is made out of concrete or has concrete. And so through this research, we will be analyzing and visually displaying through MATLAB the influence of transverse and longitudinal reinforcement on the behavior of a concrete column when it's subjected to certain loads. And so for the background and the problem of this research, we know that concrete is a brittle material, which means that it is pretty strong in compression, but it's pretty brittle in tension. And so when we apply a lot of force to concrete, it will break pretty fast. And so steel, on the other hand, is pretty strong and it's pretty ductile. So when we apply load onto steel, it will be able to sustain that load for a long time and permanently form. And so adding steel to the concrete will add strength and ductility to it. So it's important to ensure that the amount and the configuration of the steel that we're adding into the concrete is enough to support loadings within the structure. And that loading can come in the form of seismic movement from earthquakes or loadings from like the top floors, or maybe even like live loads, just like humans walking around on the upper floors. And so we can use the theoretical model for the stress-strain relation of confined concrete proposed by Manders to analyze the performance of circular and rectangular shaped columns under compression. And by doing this, we can establish the relationship between the differing amounts of reinforcement and the overall performance of the column. And we can later on, we can show this performance through a stress-strain curve. And so to perform these things, we will first look at Manders' paper. In his paper, he includes a lot of formulas and a lot of variables. And those formulas are based on mathematically theoretical principles that have been reinforced by decades of reports. And so this is pretty credible. And using his paper, we can create a MATLAB code for a member with a circular cross-section, and then find the relationship between the concrete stress and the reinforcement. And we can do the same thing for a rectangular cross-section. And in the end, we'll make conclusions about the data. And so this formula here, at the top, is the most important formula in his paper, which will allow us to find the compressive concrete stress given a compressive strain. And so these are the cross-sections for the columns that we'll be analyzing, and these variables are pretty important. We have to include them in the code. And for the later figures, the most important parameter that we'll be analyzing will be this S value, which is the center-to-center spacing between the transverse hoops. And so going on to the results, this first figure here is the stress-strain curve of a circular concrete column with a 20-inch diameter with increased spacings, as you see in the legend. And if you increase or decrease the diameter, the behavior should look pretty similar. Some notable features that we have to point out in the stress-strain curve is the ultimate compressive strength, which is the maximum point on this curve, and also the fracture strain right here, which is the strain at which the first hoop fracture occurs. And also this unconfined concrete curve right here, it's different than the other curves because at a strain of around 0.004, we'll have a downward slope towards the Spalding strain. And the same behavior can be seen with a rectangular or a square concrete column. In this figure, this column is an 18-inch by 18-inch square cross section with no cross ties. And what cross ties are it's basically a transverse reinforcement connecting two opposite longitudinal reinforcement. And we'll show later that it's pretty important in the configuration of a rectangular cross section. And so at the two notable features that I pointed out earlier, I can show the behavior between the compressive strength and the transverse reinforcement spacing, and also the transverse reinforcement fracture strain and spacing. And so as you see, as the spacing increases, the compressive strength exponentially decreases. And similar for the fracture strain, it exponentially decreases as the spacing increases. And then lastly, for this third figure here, we wanted to demonstrate the relationship between the cross ties and the strength of the rectangular cross section. As you can see, as we add more cross ties, the compressive strength increases as well as the fracture strain. So adding cross ties adds more ductility to the cross section. And then for our discussion, for the first two figures, for the circular cross section, increasing the center-to-center spacing between the hoops leads to a weakening of the column, as you saw with the decrease of the compressive strength and the fracture strain. And the same behavior can be seen with the rectangular cross section. And then also, the relationship between the compressive strength and the spacings can be modeled using MATLAB with the best fit curve, and the relationship can be seen with this equation right here. And similar for the fracture strain and the spacings, an equation was found using MATLAB. And lastly, for this third figure here, increasing the cross ties increases the number of longitudinal bars that are effectively confined, which then overall increases the compressive strength of the column. So in conclusion, the compressive strength as well as the ultimate strain or the fracture strain increases as the center-to-center spacing between the hoop bars decreases. And adding cross ties prevents the buckling of longitudinal bars, which then increases the strength of the rectangular column. So overall, our results show that adding more steel reinforcement, either transverse or longitudinal, we can strengthen the column and make it more ductile, since it can resist more loads and sustain a higher strain before it fractures. So using Mander's theoretical model, we can create a material model for concrete and steel that will be able to predict and display the behavior of the material when it's subjected to loading and unloadings. And also a pushover analysis can be performed to show the moment required when a beam of a certain cross-section is subjected to a curvature. So when you have a beam and you subject it to a moment, it will bend, and we can show that relation on MATLAB with a moment versus curvature plot. So I just want to thank Luca for meeting up with me every week and teaching me new things to help with this research. And I wanted to thank the GEAR program and Professor Xing for providing this research opportunity. And also, I didn't include it, but thank you to Ved for checking up on me once in a while, and also doing the peer edits for this poster and other papers.